Hi everybody. In this lecture I'm going to cover 11.2 in the book. The title of it is Matrices. Excuse me, it's Matrix Representations of Graphs. There's a quick thing I want to say about graphs first, and then we'll actually jump into that. Just some terminology about different kinds of graphs. I think there's one sort of graph that's it makes sense to people where there's a directionality to the edges. So for instance, a little cycle of things. You might be familiar with the game where was it scissors breaks paper and paper covers rock and rock smashes scissors. So there's names for the nodes and there's also names for the arrows that are directed here. That's a kind of graph that's known as a directed graph or a digraph. That happens to be a simple digraph. You can have digraphs that have more features. For instance, you might have multiple one-way streets between objects, and that actually happens in reality. There's certain blocks in New Haven where all the streets seem to go one way in the same direction. And, anyway, digraphs. So it's just a contraction of directed and graph. There are simple graphs. If I just had an undirected graph that had the same nodes and the same edges, but for the fact that they've got no arrows on them, this would be called a simple undirected graph. If you want to really specify that it's not a digraph, you say undirected. But if you don't say anything, people ordinarily think this is the kind of graph you're talking about. So that's the usage I do. If it's simple, I'll just say a graph. If it's directed, I'll say a digraph. And the one other piece of terminology we should look at is when you have that multiplicity I was talking about. Maybe you have a graph with 3 edges between those guys, but only 1 between these other 2. That is known as a multigraph. I'm not really sure whether there's a hyphen there or not, so it's either 2 words. No, it must be, it's either 1 word or it's got a hyphen. But in any case, a multigraph is how you say it. Okay, so directed graphs, ordinary graphs, undirected, multigraphs. Those are the 3 things that we're going to distinguish when we start talking about matrices, because when you're looking at matrices, you can tell the difference between these things. You can look at a table of numbers and know whether you're dealing with a multigraph, a digraph, or a regular graph. Right, so I just said some things about matrices. Oh yeah, that's worth making a point. The singular version of this word comes from the Latin matrix. Pluralized, it's matrices. There's a few words in English, more typically in Romance languages, you'll find words that are cognates of that. The maitre d' at a restaurant is somebody who takes you to your table. Well, actually, I think I may have that wrong, because that might be the master version of it. Anyway, regardless of etymology, the word means a table for us. A matrix is a table of numbers. There's a movie called, or actually a series of movies, it's kind of dated at this point, I suppose, called The Matrix. And when I was a grad student in Chicago, there was this advertising campaign for the movie series, or for the first one of the movies. And it featured these flat black billboards, and in white print it said, "What is the Matrix?" Question mark, right? And people were talking about it, but us grad students were like, we know this, we got it. It's a table of numbers. Of course, in the movies it was like a computer simulated world where they kept human beings prisoner, but whatever. It really isn't that. It's a table of numbers for us. So why do I want to talk about matrices in the context of graphs? Well, you can think of a matrix just as a data structure, honestly. It's a two-dimensional version of a list, and that means that you've got sort of an indexing set for the rows, and then also an indexing set for the columns. Now, typically the indexing sets are just the numbers 1 to whatever. So let me just write down a matrix. I happen to like 0-1 matrices because I'm a coding theorist, and that's what I work with all my life. So I was trying to write down a random matrix, and it ended up just having zeros and ones in it. My bad, but honestly, these could be anything. They could be real numbers. I've picked integers. I've actually picked binary integers. But yeah, you could have other things in there. So in this example, if we say this is matrix A, then the entry that's in the first row and first column would be expressed like that, a little subscript, and actually a pair of subscripts. Often this comma between them is elided if if it's clear that if you had fewer than 11 entries, you could just realize this was 1-1 and you'd be fine with it. All right, so what is A11? It's this number that's in the first row and first column. Notice that the columns and the rows are numbered 1, 2, 3, and 1, 2, 3 for the rows. Usually with lists, we start numbering at 0, but for whatever reason, people tend to use a 1-based numbering system for the entries in a matrix. It wouldn't be that hard to switch back to the other ones, and in fact, in a certain way, it makes address arithmetic easier, but that's fine. Let's see, give you another entry in this. How about if we went the 1, 2 entry? Well, we got lucky with the 1, 2 entry because that's the 1, 2 entry, but if we were confused and thought it was this one, you'd still get a 0. So I guess in that case, it's 0, whether we're confused or not. Why is it this way? This one, not that one. It's because when we're writing these indices, it's row first, then column. So the sort of y coordinate into the thing, and then the x coordinate. Good with that? So there's a 1 in the upper right corner. What are the indices to that 1? That's row 1, column 3, so that would be A13. Oh, I realize I'm doing something a little bit different from in the book. Yeah, and this is probably worth making sure we follow the same convention. In the book, the matrix is represented by a capital letter, so we always use capital letters for our matrices. But the entries for the matrix would be written with the same letter except lowercase. So I should fix this. That should really be little a's here, here, and here. But little a entries go with big A as the matrix. It's sort of a way to refer to the whole table versus a way to refer to the individual entries in it. I'm not going to fill out what are the rest of the entries in that thing, but it's certainly something that I think everybody can handle. Just remember this, rows first, then columns. Right, so why is such a table of numbers the right thing to encapsulate a graph? Well, why don't we do an example? I'm going to draw a graph and then show you how to construct the matrix that it's represented by. All right, that's my graph. It's got 3 vertices and 1, 2, 3, 4 edges. It's clearly a multi-graph, right? There's a multiple edge there. It's got a loop as well. So it's in that family. Let's build the matrix that goes with it. The matrix is called the adjacency matrix. There is another matrix known as the incidence matrix, but we're not going to be looking at that. Well, maybe I will actually just briefly at the end of this, because there's some nice matrix analogs between the adjacency and the incidence matrix. Anyway, for now, what we're going to do is make a matrix whose rows and columns are indexed by the vertices. So you think about, in this case, it'll be a 3 by 3 table. I don't want to give the impression these tables are always 3 by 3. The last example I did was 3 by 3 too. That was just a coincidence. They can be any size. But anyway, we'll have V1, V2, V3 for the column entries, and V1, V2, V3, sort of the indices or the pointers into the array. Now, V1 and V2 do not have loops at them, so we'll write a 0 right here at the V1, V1 entry, and the V2, V2 entry, also a 0. But V3 does have a loop. A loop appears as a non-zero number somewhere on the diagonal of the thing. Right? So this, what numbers are we actually sticking in? If you have an edge that goes from a vertex to another vertex, you count it up in the Vi to Vj entry. So for instance, see how I had 2 edges that go from V1 to V2? I put a 2 right there. From V1 to V2, I have 2 edges. Now, these are not directed edges, right? There's no arrows on them. So it's also true that from V2 to V1, I have 2 entries, 2 edges. There's one other edge that I haven't dealt with. These 2's represent those 2 edges. That one edge, that one loop is represented by that one there. What about this edge that goes between V2 and V3? From V3 to V2, there's one edge, and also from V2 to V3, there's one edge. Everywhere else, it's 0. Well, it's not too many everywheres. Right, from V1 to V3, did we see an edge? Nah, there's no connection there. And similarly, V3 to V1. This kind of matrix is known as a symmetric matrix. And it's symmetric across its diagonal. If you look at entries like that, the diagonal is this line right here. You see how the entries are always the same if they're on opposite sides of the diagonal, the same distance out. So why is this symmetric? It's because of the matrix properties of this thing. This is undirected. If we had some directions on these things, we might have different numbers of things, for instance, from V1 to V2 as from V2 to V1. But since our edges are undirected, the matrix comes out symmetric. Okay, here's another example. This is a directed graph. You can tell because you see arrows on everybody. A digraph with 5 vertices. I'll point out that before I labeled the columns and the rows of our matrix with the actual vertex names, but it's enough to just say the numbers. So here I'm just going to say what the numbers are. In fact, maybe it's enough to just count in our head. But there's going to be 5 entries, or 5 columns, and there's going to be 5 rows. Have I made this big enough? Let's see. Not quite. I think I need to go a little lower. All right. So, well, and let me do a similar, space things out nicely. All right. From vertex 1 to vertex 2, we're seeing an edge. So in the 1, 2 position, we've got one edge. Let's see, this is, we just took care of that edge. Oh, let's do this one next. From vertex 1 to vertex 5, we see an edge. That's in the 1, 5 position. There's an edge. I'm not sure if these little dashes I made need to be quite so big, and they were guidelines, right? So that if you're working on ruled paper, that would be easier to deal with, at least for the rows. All right, so we've got vertex 1's edges dealt with, both the one from it to 2 and the one from it to 5. Is there any other edges that go from vertex 1 to, say, 3 or 4? Well, no, there isn't. Is there any edge that goes from vertex 1 to itself? No, there isn't. So we got zeros in the remaining positions in that first row. Let's see, vertex 2 has a single edge leaving it, and that goes to vertex 3. So in the 2, 3 position, you see a 1. And you see how it's going to be zeros everywhere else in that matrix. It seems like graphs like 0, 1 matrices just the way I do. Actually, might as well point that out. Why are these matrices all turning out to be zeros and ones? Because these are simple directed graphs. There's no multi-edges. Right? So if there were multiple paths from V1 to V5, I might have a 2 or a 3 here, but since it's either there or not in this particular graph, it's only zeros or ones. Let's see. All right, what about 3? 3 has a single edge leaving it, and it goes to 5. You notice how filling this out in a sort of do the rows first, to work across the rows and then work your way down is kind of handy. So really, it's 0 everywhere else? Well, there's no edge to 1, there's no edge to 2. The edge goes the other way from between 3 and 2. And there's no edge to 4. Yeah, just that one. So the remaining entries in this row are zeros. 4 has one thing leaving it, and it goes to 3. Okay, this is 4. 1, 2, 3. And so zeros everywhere else in that row too. And lastly, row 5. Oh, wow, 5 is kind of at the tail end of this whole thing. It didn't get anything, so that's an entire row of zeros. There's no edges that go from 5 to somewhere else. So I didn't make that bracket long enough. All right, I started to check off what things have been said, but there's 3 edges in here that I didn't mark. So we took care of row 1. That was all the edges that leave V1. V2 has this 1 in the 3rd position. That's dealt with. V3 has a 1 in the 5th position because there's an edge from 3 to 5. So that one's dealt with. And the last one should be this, which goes from row 4 to column 3. It's going from 4 to 3. Cool. We dealt with all the edges properly. So that is the adjacency matrix of our graph. It's what's known as a sparse matrix, by the way. It's got mostly 0 entries. There's only a few ones in it. Relatively speaking, you could say the number of non-zero entries tells you about how complex the graph is. There's a couple of things that you can point out about the matrix that tell you information about the graph. So we might as well see those here. Look at the matrix entries that are here along its diagonal. That's called the main diagonal of the graph. They're all zeros. What does that tell you about the graph itself? So just looking at the table, you would know that the graph had no loops in it. The entries here, because this is simple and directed, you always see a pairing across the diagonal of a 1 and a 0. I was thinking that the entries should be skew symmetric or anti-symmetric. That is, a 1 here would mean a -1 there, but that's not right. See, if you've got a 1 here, you'll have a 0 in the other position. 1, 0, 1, 0, and 1, 0. See, you see how the 1s are always paired with zeros? It's not true that zeros are always paired with 1s, right? There's plenty of places where you'll have symmetry across the diagonal where zeros are matched with zeros, but wherever you have a 1, you get a 0 the other way. You can have directed graphs that have sort of multi-edges because we consider the edges different. So what if I had a parallel edge to that one, but its orientation was the other way around? Then I could get the non-symmetry. So this is still part of considered a simple directed graph, but there's some categories of graphs where the directionality is one way only one-way streets on a graph. This is now an example of one where there is a two-way street somewhere. Between 3 and 5, we can go both directions. Certain physical phenomena, that makes sense. Like if these are cities, and cities probably would always have two-way streets between them, but intersections in a city, there might be two different routes between two intersections and going in either direction, or there might be a single direction that goes from one intersection to the other. So that could happen. But if this was supposed to be a game outcome graph, like the scissor paper rock, this would have to be the scissor paper rock lizard Spock version, and it's not. But it wouldn't make sense to have the two-way streets there. You want the graph to tell you who wins, and it's not a tie. It's not supposed to be a tie. Yeah. Let me just point out where we would change things to make this kind of thing happen. If we wanted to have an edge from 5 to 3, well, we go to row 5, find column 3, and we would put a 1 there. And I think we just broke the always zeros across from the ones thing, right? This one and that one are across from one another. So you can, there's a little bit tough to spot, but you can tell whether you've got parallel edges. I probably should say anti-parallel because they go in opposite directions on a directed graph thing by seeing whether you ever have the ones across from ones. Okay, so I've written a great huge matrix on the board here. This is a 6 by 6 matrix. Adjacency matrices are always what are called square, meaning the same number of columns as there are, same number of columns as there are rows. But this matrix has some extra structure on it, and this is something you should learn to look for in a matrix. It's called block structure. And basically it's that there are big chunks of this that are all zeros. And you want to look for sort of the biggest square or at least rectangular chunks you can find that are all zeros. I'll just indicate one of them is right here. That's a whole block of zeros. And then there's another block of zeros down below. So often when you are indicating that to somebody that a matrix has this sort of block structure where there's big areas that are all zeros, you wouldn't draw it the way I have done here. Let me just modify this. Let's erase out our block. All those zeros are gone. Let's get rid of this other block. And you put some thin lines down the matrix. Sometimes these are dashed lines, actually. Telling it, yeah, break it up into these 4 subcomponents. And a big zero inside of a block tells you that that's a all zeros block. Okay. So we've got a matrix now that's got this block form, and it's really spelled out to us right here. There's a little 3 by 3 part up in the upper left, and then there's a 3 by 3 part in the bottom right. And let's think about what this means for a graph. Well, can I draw the graph over here on the side? I'm going to have vertices 1, 2, and 3 really separated from vertices 4, 5, and 6. Why the separation? Because these zeros are all the connections that go from somebody in the 4, 5, 6 group to somebody in the 1, 2, 3 group. So these zeros are saying there's no connections that go from 4, 5, 6 to 1, 2, 3. And these zeros are telling you the same thing the other way around, that nothing in the ones labeled 1, 2, 3 is connected to anything, these zeros, and nothing in the 1, 2, 3 is connected to anything in the 4, 5, 6 positions. So the graph falls apart. Now let's see, we can go ahead and figure out what the 1, 2, 3 graph has going on in it. There's a loop at vertex 1, and there's a loop at vertex 3. That's those two ones. There's 2 edges from 1 to 3. There are not 2 edges from 3 to 1, so that must be that these are directed then. I guess my loops have to be directed too, although honestly for a loop it doesn't matter whether it's directed. And what else do we have? This one here, that's in the 2 to no, sorry, yeah, that's in the 2 to 1. There's a direction arrow from 2 to 1, and finally there's an arrow from 3 to 2. Right. So I guess we're in a directed graph. We should be drawing arrows, but you'll notice this submatrix is symmetric. Now, here's where interpretation comes in. Is it symmetric because there are two undirected edges between the two things? Or is it symmetric because it just happens to be? It's really a directed graphs matrix. I would say that since this part is directed, and clearly is directed, the overall matrix does not have the symmetry that shows you that you're dealing with an undirected graph. So we should interpret that stuff the other way. All right, I'm going to take care of the loop at 6 first. Right, there's a loop at 6. How about we deal with these other ones in the thing too? That one in the, actually, which row is this? 5. From 5 to 6, there's a direction arrow. And from 6, row 6, to row 5, to column 5, there's a directed arrow. So I guess I should draw it like this. There's a two-way connection between those guys. Then what do these 2's tell us? Oh, it's awful. From 4 to 5, there's 2 one-way streets that go in the same direction from 4 to 5. And then from 5 to 4, there's 2 more. Well, that's a really kind of ugly graph. Sorry, I didn't mean it for it to be that ugly, but there it is. Right? But the main point is you see that it's disconnected. There's these 2 different components, or some people would say connected components of the graph. Awesome. So structures in the graph, I said that wrong. Structures in the matrix are reflected as structural things about the graph, and vice versa. If you know the graph is something that falls into 2 pieces, you should probably label the vertices in a reasonable way so that the graph ends up showing that block structure. It's a little bit hard to spot the block structure if the stuff is all alternating back and forth. Like if I call these 1, 2, 3, 4, 5, 6, then these zeros would actually be spread out like a checkerboard, and it would be hard to spot them. The fact that I laid them out with 1, 2, 3 all connected to each other and 4, 5, 6 all connected to each other is why that structure looks the way it does. If it was just the case that matrices were something we use to sort of as a data structure to hold the contents of a graph in computer storage, that'd probably be enough of a reason to think about matrices, to study them. But there's actually much more going on. Matrices are extremely powerful tools in a lot of ways. For instance, many physical quantities are better captured as a matrix than as a vector or a single number. I think almost everybody here knows that certain things are vector quantities. They have a direction to them as well as a size. Some things are just represented by a size, but the amount a person weighs is just a single number, although the force of gravity has a direction to it, it goes down. Matrices are a category of things, or represent a category of things known as tensors. So there's certain quantities that are more than just directional. The classic example of a tensor is the way stress works inside of a body that's being deformed. If you have some hunk of metal and it's being acted on by external forces to twist it or compress it, or maybe combinations of those, it's actually a matrix that represents at each point in it how it's being pushed on. In computer graphics, you'll see matrices used to make transformations of the points in a scene. So they're all over the place, and honestly, once you get into doing matrices, you see them like everywhere. Okay, so one of the things that matrices allow us to do, which wouldn't be obvious at all from the context we've seen them first as containers for the information about a graph, but you can multiply them. That is, you can take a table of numbers and times it by another table of numbers, and you make a reasonable output thing that is, again, a table of numbers. This is sort of funny, and it takes a little bit of getting used to. It turns matrices into something known as an algebra. In math and algebra, when you use it like that, with the indefinite article, is a structure that has the same kind of structure as vectors, where you can add things and you can multiply them by numbers. That's how vectors work. But in an algebra, you can also multiply the vectors. You can multiply two matrices together and get another matrix. So how does matrix multiplication work? It seems rather confusing at first, but I just want you to remember this mantra: rows into columns. So if you say rows into columns when you're thinking about having to multiply two matrices, you'll be set on matrices. There's also a bit that you have to get used to, which is a little bit like, you know that thing where you pat your head at the same time you rub your belly? It's hard to do. We've got to make our two hands do something totally different. And the two things are the rows and the columns. So rows go side to side, columns go vertically. Just practice for a second that you can make your left hand go sideways while you make your right hand go vertically, pointing at stuff, right? It's a little weird because sometimes your hand wants to twist and go the other way, but rows, columns, we're just tracing things like that. Okay. There is an issue that's known as conformability. Fancy word, but it just means the rows that you're putting the columns into, these things have to be the same size. The rows of one matrix, let's call the rows, the first matrix A, they have to have the same length as the columns of B. The columns of B. That's it. As long as you have the length of these guys, the first guy's rows is equal to the length of the second guy's columns, you have conformability, and that means that it's possible to multiply. This is what you need. This is the condition that you need to be able to multiply two tables. The length of the rows of one has to equal the length of the columns of the other. So it's probably worth doing this in a pictorial way. If A is m by n, and when I say that the matrix is m by n, I'm talking about how many rows it has and how many columns it has. It's always rows first, then columns second. And suppose B is, and two new letters, how about P by Q? This idea of conformability is that I want the rows of this matrix to have the same length as the columns of this matrix. Well, which of these numbers here is the length of the rows? That m is telling me how many rows I have. The number of columns is the length of the row. You get that? This n here is the number of columns, but it's also the length of the rows. If that doesn't make sense to you, pause the video for a second and just, draw a few matrices and then you convince yourself that's true. What we've got here, I'm going to look at P. That's the number of rows in this matrix, but what is it also as a length? It's the length of the columns. The number of entries in the columns. So this idea for conformability that the rows of one matrix have to equal in length the columns of the other is that these two things have to be the same, right? So it's what are often called the inside dimensions. P and N need to be equal. That's kind of an ugly way to write it. Let me write that a little better, because it doesn't take much. You look at the size of the first matrix, m by n, and you think about multiplying that times the size of the second matrix, p by q. These things have to match. In that way of writing it, perhaps you see why they're called the inside dimensions. Okay, so let's do an example. I think a 2 by 2 is probably the best place to start. So I'm just gonna write down two matrices. 1, 2, 3, 1. Just keep the numbers small, because you don't want to play this game with too big of stuff at first. How about 0, 1, 1, 2. Okay, so like I said, we're going to be tracing rows with one hand and columns with the other. Why and what are we doing while we trace that? As you trace, multiply corresponding entries. And as you trace, well, I should say the whole sentence, multiply corresponding entries and basically keep a running total of what you're getting as these products. So this is quite physical. I'm going to trace a row of this matrix and a column of this matrix, and we'll multiply and we'll add as we go. So first I get a 1 times a 0, and then I get a 2 times a 1. When it's just they're both 2 by 2, the thing isn't very long, and so that's good. 1 times 0, 2 times 1. The entry I just got, 1 times 0 plus 2 times 1, is what goes in. Which row was I tracing? The first one. And which column was I chasing? The first one. So that's your A11, as it were. I don't know if I want to call it A, because I was sort of thinking of this one as A. Suppose we say that's A, and this is B, and the answer is C. Then this would be C11, the number you get in the 1-1 position. But it's sort of just easier, in my opinion, rather than keeping track of the coefficients, is say, we're trying to fill out this thing. And this is going to be a 2 by 2 as well. And I want to know what goes in that first position. That's the 1-1 position. So I trace row 1 and column 1. And I get the number that I just did, which is, what is that? 2. If that's not clear, let me do another randomly chosen position in this matrix. Suppose I wanted the 2-2 position in C. Then I would need to trace row 2 here and column 2 here. 3 plus 2. It's a 5, apparently. If I was keeping track of things with the coefficients, what I would just said was C22 is equal to, what was it again? 3 times 1 plus 1 times 2. That is indeed 5, but like I said, if you do it in your head, it's probably quicker and more than doable. All right, how about if I wanted to get that position? That is row 1, column 2. So I'll need row 1 and column 2. Trace 1 times 1 plus 2 times 2. Oh, we're also a 5. That was C12 equals 1 times 1 plus 2 times 2. Wait, was it 1 times 1 plus 2 times 2? Yeah, that's weird. It's kind of funny that the row of this one is equal to the column of that one, or that the entries are the same. How about this last position? That's in row 2, column 1. So I'm going to need row 2 over here, column 1 over here, and I get 3 times 0 plus 1 times 1. That's easy, it's 1. I just did that right. Just make sure I copied right. 3 times 0 plus 1 times 1. Yeah. Wow, there's something that I knew and I sort of faked in this example, which is, how did I know this was going to be a 2 by 2 answer? And that's visible also in the conformability calculation. What we have here is a 2 by 2 times a 2 by 2. So those numbers have to match, and they do. And these actually give you the size of the answer. So I'm going to erase and put up another example of matrix multiplication where the inside dimensions will match and the outside dimensions aren't going to just be 2 by 3. Okay. All right, so here's an example for us to do some matrix multiplying with. First, let's check the conformability. Now, I tend to just do the tracing. Rows are length 2, columns are length 2. So the rows into columns mantra is going to work out. If you want to think about the size computation, what size is this matrix? It's a 3-row, 2-column matrix. And this matrix has 2 rows but 4 columns. So the 2's on the inside match, and the answer is going to be a 3 by 4. So if we call them A, B, and C, C is a 4 by 4 matrix. I'm just going to make a big enough table that I can put in, what did I say, 3 rows and 4 columns. I'm going to make some little marks so I keep everybody lined up, because that's hard for me to do sometimes. All right, let's do our rows into columns bit. If I want the 1, 1 position, I do row 1 with column 1, and I'm going to maybe start going a little faster. 1 times 1 plus 2 times 0, that's a 1. If I want the row 1 column 2 position, that's this row 1 with this column 2. That's 0 plus 2. How about well, let me skip around, because I don't want you, it gets boring when you do all the way across one row, although in practice, it's probably the smart way to go. Just do all a row, that is, you're not moving from which row you're tracing until you move to the next row. But I'm going to do row 3, column 2. That is 3 times 0 plus 1 times 1. Okay, that's a 1. 0 plus 1. 1. Where do I put it? I looked at row 3 and column 2. So this is 3, 2. There's a 1 right there. If I wanted to get the entry down here in the middle on the end, what would I have to do? That's in the second row, 4th column of that matrix, of the answer matrix. So I'm going to trace the second row and the 4th column, and I get 2 times 1 plus 0 times 2. I get a 2. Seem to be bad at erasing with my finger. All right, so so I've done enough of the playing around so that you get the sense of where the things from. Let me get serious, buckle down a little bit, and take them in order. We've already done row 1 with columns 1 and 2. How about row 1 with column 3? That's 2 plus 4, okay, 6. And row 1, column 4 is 1 plus 4, 5. Now the ones involving row 2. 2 plus 0. 2 and 0. Okay, 2. 0 and 0. What? Can it come out 0? Well, apparently it can. Row 2, column 3, 4 plus 0. I'm going to rewrite that one because it's a little bit not lined up. All right. And lastly, the things in the bottom row of our answer that come from row 3 into the various columns of the other matrix. So the 3, 1 thing is 3 plus 0. 0 plus 1. Oh, we already did that. 6 plus 2. And 3 plus 2. I was just noticing something weird. Do you see how 1, 2, 3 and 2, 0, 1 have appeared in our answer? The columns of that guy are actually visible right here in our matrix. And I don't know what those other guys are, but it's interesting that these columns have just shown up in our matrix. Why? Why did they do that? It's because of the special form of that matrix had in the first 2 positions. This also has what I would call a block structure. The matrix up front has this special character that it's got a 1 in one position and zeros in the other. In fact, the 1s are on the diagonal and the zeros are off. That's interesting. Now, neither of these could be adjacency matrices, right? Because if they were, they'd be square. It'd be a 3 by 3 or a 2 by 2, but these are not square, so they couldn't be adjacency matrices. They could be what I talked about before, incidence matrices. Incidence matrices are gotten when you show the incidence between vertices and edges. So since there are a different number of edges as there are vertices, one can, how to say that? One can have different non-square sizes for such matrices. But in incidence matrices, you never see anything but 1s and 0s. Again, following my personal prejudice towards binary. But because incidence, a relationship between edges and vertices, is a binary thing. Either the edge is incident with the vertex, that is, it touches it, or it does not. So an incidence matrix is actually pretty interesting. It's all 0s and 1s, and it's actually also always got just 2 1s in every column, because every edge has 2 endpoints. Oh, wait, what if a endpoint is there twice? Oh, I see. If you have graphs with loops, I think the incidence matrix can become more complicated. Maybe have 2s in the entries. But here's a matrix multiplication problem it's almost like it's too simple and it makes it feel hard because it's simple. But let's just run through it, because this is a very important special case of our multiplying of matrices. So what's the size computation we would do? The first matrix has 1 row, 3 columns. And so it's a 1 by 3. Multiply it with, what's the size of the second one? It's 3 rows and a single column. 3 by 1. Well, those 3's match, but the answer is going to be 1 by 1. Now, people typically don't think of putting having a table when it's only got 1 row and 1 column. You usually think of that's just a number. Forget the braces on the outside of it. You've got a single number. So this kind of a matrix product is known as the scalar product, or also dot product. I mentioned before the difference between scalars and vectors. How long something is, how heavy something is, how much electric charge something has. Those are scalar quantities. They have a size associated, but they have no direction associated. Which way the wind is going, north-northeast at 10 miles an hour, or the strength of, or I shouldn't say strength, the magnetic field inside an MRI machine, that's got a directionality as well as an intensity. So those are vector quantities, but scalars are 1 by 1 matrices, or just ordinary real numbers. All right, so when I do this scalar product here, I'm going to get a single number. I'm going to get a 1 by 1 table. Let's do it. there's one row to trace and there's one column to trace, so I just get this really nice 1 times 2 plus 2 times 3 plus 0 times 1. Oh crap, I didn't keep track. 2 plus 6 and 0. That's an 8. So we've got the dot product of two vectors. Actually, that's what we're doing here. This vector is written as a row vector, this vector is a column vector, and you get the dot product. Often, if you're going on to linear algebra, they would call this V times W transpose. The transpose means take it as a row and turn it 90 degrees and so it looks like a column. But if you have a single row and a single column, you're getting a scalar product. You're getting a single entry out of it. A lot of people, and I actually prefer this direction, but it seemed like it required too much lead in. This is really what we're doing when we do the rows in the column bit, right? So what we're doing when we do the matrix multiplication is sort of thinking of one matrix being broken up into rows, the other broken up into columns, and then we're doing scalar products for every row and every column. So that's probably a good idea for me to illustrate that with one last quick example. All right, so I've written a couple of 3x3 matrices, and I want to talk about thinking about this product as a collection of dot products we're actually doing. So what you want to do is sort of think about putting in little dividing lines into this first matrix so that it's broken up into 3 rows. And into this second matrix, you'll put in little dividers to break it up into 3 columns. And then the product is something like row 1 times column 1 in that position, and row 1 times column 2 in that position, and then row 1 times column 3 in that position. And I'm going to quickly fill out the rest of it. Row 2, column 1, row 2, column 2, row 2, column 3. I hope this little shorthand I'm using makes sense to everybody. Row 3, column 1, row 3, column 2, row 3, column 3. There's some symmetries to notice in the way these products work. You see how across the row of the answer, we always see the ones. The first row has ones on the R. Across the columns, the first column has all the ones on the C. The 2's and the C's on the second column, and the 3's on the C's in the third column. This all makes sense. So that's the form of the answer. Why don't we go ahead and actually compute, though? What do we get when we dot or scalar product the rows with the columns of this thing? 0 plus 1 plus 4, that's a 5. 0 plus 0 plus 2, that's a 2. 0 plus 1 plus 0, that's a 1. All right, row 2 columns with other columns, that's 0 plus 0 plus 2. 1 plus 0 plus 1. 2 plus 0 plus 0. One last row with the 3 columns to go with. Let's see, 0 plus 1 plus 0. That's a 1. Like my brace didn't get long enough. 2 plus 0 plus 0. And finally, 4 plus 1 plus 0. 4, that's 5. Okay, so not by coincidence, you should notice that the matrix, both of these matrices are the same, as they're equal. Oh, I don't think we ever said what does it mean to say 2 matrices are equal? Well, you're looking at it. They have to be the same size, first off, and every single entry in one matrix has to be equal to the corresponding matrix entry in the other. So, those 2 things are zeros. These 2 things are ones. Those 2 things are twos. The ij entry in each one is the same as the ij entry in the other. All right, and so if we called this matrix A, what we did was A times A. Well, this answer is called A squared. That is, you can now sort of do polynomial stuff with a matrix. You can figure out what its square is and what its cube is and so on. If I wanted the cube, what would I do? I take this thing and times it by another one of these. And that begs an interesting question. Matrix multiplication is normally what's called non-commutative, meaning doing A times B, not necessarily the same thing as B times A. For instance, A times B might be possible because they're conformable, but if you switch the order, it wouldn't be conformable. You can't even multiply. But even if they are conformable in both directions, you often will get a completely different answer. AB times BA is not usually the same. But A times A always is the same, and any power of A is always the same whether you do it in one order versus the other. So that's kind of a nice feature, that the powers of a single matrix are always well defined. That is, A cubed, there might be this possibility that A squared times A to the 1 is different from A to the 1 times A squared. Fortunately, it doesn't work out that way. So A cubed is just one possibility. Okay, so why did I pick on this? Well, I want you to look at the graph that corresponds to this matrix A. Let's draw it upstairs. It's going to have 3 vertices, right? And there's zeros down the diagonal, so we've got no loops. I've got ones across the diagonal in the 1, 2 position and also in the 2, 1 position. So that means vertex 1 and vertex 2 have an edge between them. What does this 2 that's here and here symmetrically tell us? Between 1 and 3, there's 2 edges. And what else? There's a pair of ones here and here. That's between, that's the third edge to the third vertex to the second vertex, or the second one to the third. So 2 and 3 have an edge between them. Now, these numbers actually count something else. They tell you how many paths there are to get from one vertex to the other, right? So a walk, actually it's just a walk of length 1, but this fact that I could go 2 ways here from 1 to 3 is represented by that 2 in there. What is going on in the square in that same position, 1, 3 position? That's position 1, column 3. We're getting a 1. Well, I'll just jump to the punchline. The square tells you how many paths there are of length, whatever the power is. So for square, it's length 2 paths. How many ways are there to get from 1 to 3 taking a walk of length 2? You got to go over here and come back to here. You can't do this and back because you haven't got it to 3. The only route of length 2 from 1 to 3 is that one. That's what that 1 represents. And if you reverse that route from 3 to 2 back to 1, you've got a walk of length 2 that goes from 3 to 1. What are these 5s? Well, that 5 is on the diagonal. It's in the 1, 1 position. So it tells me how many ways can I take a walk of length 2 from 1 to itself. I could go over to 2 and back. I can go down to 3 and back on the same edge, down to 3 and back on the other edge, down to 3 left and then right, or right and then left. There really are 5 different walks from between 1 and itself on that graph. So we dealt with that one. What about the 2's? Let's look at the 2's in this product. Okay, that's in position 1, 2, right? So how many ways can I take a walk of length 2 going from 1 to 2? I can't go directly because then I'd have to leave if it's going to be length 2. But I can go down to 3 and then over, and I can get to 3 in 2 different ways. So you see how you get 2 for the total number of walks of length 2? I feel like we just got to work out what's A cubed and see how that plays out, because it's kind of neat and amazing. And yeah, All right, so I'm gonna erase this part, and we'll and some of these extra marks I put on there. We're gonna calculate a cubed, which means I need a squared to go in here. Right, I had to take a second and recalculate a squared because I'd accidentally erased it before I had it to write again. So, but anyway, that's a and that's a squared. So if I multiply these two things, I should get the entries of a cubed. And it's good practice, I suppose, to keep doing this. I often don't need to write those dividing lines because I've gotten pretty good at tracing rows and columns with my separate hands. 0 plus 2 plus 2, that's a 4 in that position. 0 plus 2 plus 4, that's a 6 here. And 0 plus 2 plus 10, wow, 12. Kind of strange. By the way, I know because of the interpretation of these things that this matrix is going to come out symmetric. So I don't really need to do that entry and that entry. They'll be equal to the things that are symmetrically placed from them across the diagonal. So let's do row 2, column 2. That's 2 plus 0 plus another 2, 4. And 1 plus 0 plus 5, that's 6. Similarly, that entry must be a 6. And lastly, we have 2 plus 2 plus 0, 4. Now, returning to the graph here, sorry, I gotta relabel that. These should be the walks of length 3 between any of our guys. So for instance, this 4 tells me there are 4 different ways to take a walk of length 3 that comes from 1 and returns back to 1. One of them, for instance, is go over to 2, come down to 3, and come back to 1. In fact, you can do that in two different ways. 1 to 2 to 3, and then 2 choices for how to get back to 1. So that's 2 of them, but there's 4. What are the other ones? They've got to be length 3, right? How about I leave here along one of these guys, go over to 2, and then come back to 1. And I've got 2 choices for that. So there's sort of 2 versions of the clockwise walk from 1 to 1 of length 3, and there's 2 versions of the counterclockwise walk from 1 to 1 of length 3. Total of 4. What about 6 in that position? Well, that's how many ways we can walk from 1 to 2 with a length 3 thing. A length 3. Oh, one thing you could do is over and back, and right? You could just go over, return, and then go back. So there's one way like that. There's some kind of funny stuff you can do. You can go over to 3, and then back to 1, and then over to 2. Yeah, so let's see, I'm getting 1, 2, 3, 1, 2. Okay, so how many ways are there to go from 1 to 3 and back to 1? There's 4. I can do left side, left side, left side, right side, right side, right side, or right side, left side. So there's 4 ways to get from 1 back to 1, and then 1 way to go from there on to 2. I just took care of 4 of the possibilities. Then there's 1, 2, 1. That's a third possibility. One more, but there's 6. How else can I get from 1 to 2, taking a path of length 3, taking a walk of length 3? 4 there. I'm only seeing 4. I'm only seeing 5, not 6. I had to stop the video and check around until I finally found it. It was sort of a non-intuitive possibility. Maybe some of you have got it while I was fumbling. But you could go from 1 to 2, and then go to 2, from 2 to 3, and then back up and come back to 2. So there's dink, dink, dink. That's a walk of length 3, and that's the one that adds up the total. Makes it correct. Wow, how about this 12? Can we really get from 1 to 3, 12 different ways? Using a path of length 3. Well, let's see. I've got ones that look like this. Go over to 2, come back to 1, and then go down. And there's 2 of those. I've got things that go down and back up and then down again. Now, how many of those are there going to be? Now there's basically 8 choices for whether we go the left branch or the right branch. So there's 8 of these. Almost there, we need 2 more. What are they? I think they're things that go down here, then over to 2, and then back to 3. Right, so that would be like go down, over, and back. And there's 2 of those, because you can take the left branch or the right branch there. Do we get 12 all told? Yeah. So, if you don't trust me, work out the rest of these things, but it's pretty amazing that the powers of the adjacency matrix actually count the walks of a given length, and the length is what's the power that you're taking between vertex I and vertex J in a graph.